Hello everybody, I'm Alice Brunello, a second year PhD student from Italy. I'm doing a co-tutela program under the supervision of both Professor Gonzalo Sanchez Arriaga from Spain and Professor Enrico Lorenzini from Italy. The title of my PhD thesis is Green Space Transportation with Tether Technology and regards the use of tethers for moving in space. On October, I will fly to Spain for 3 months in order to do my compulsory outgrowth period at the UC3M, so I hope to see you soon in Madrid. In the meantime, I hope you will enjoy my presentation, and if you have any questions or curiosities, please don't hesitate to contact me. In this presentation, I will offer you a description of tether systems, and I will talk about the research project I'm investigating with a focus on the main objectives. I will offer an overview of the international project I'm involved, and I will talk about the most important achieved goals in the last year. I will describe the main results obtained both for the program ETIPAC and Iperdrone, and at least I will show the future developments I schedule for the next year. A tethered satellite is coupled by a long cable to another mast or spacecraft. Tethers can be inert or electrodynamic. Inert tethers are able to exchange angular momentum between objects in space, while electrodynamic tethers, interacting with the electrical and magnetical force field, produce green propulsion in space. A space tether can be used for deorbiting end-of-life satellites, contributing to the mitigation of the growth of orbital debris, but can be used also for producing thrust forces in space, in example for reboosting LEO orbit satellites, or for re-entering payloads from low Earth orbits through the generation of delta V offering by the swing and release technique. In the last several years, the need for an alternative to chemical propulsive system for LEO orbit satellite has become increasingly evident. A tether system can provide adequate thrust or drag without the complications of the combustion and with a minimal impact on the space environment. The research project is centered on demonstrating different configurations of tether system to overcome the limitation of the rocket propulsion, enable new classes of mission currently unaffordable or infeasible, significantly advance the tether technology towards an operational level, and establish a deeper understanding of critical processes and technologies for improving tether system in the future. The final goal will be to demonstrate the capability of the tether technology to provide a robust, safe, and propellant-less propulsion, both as the orbiting and orbit-raising device, and fully characterize the performances of an integrated tether propulsion system. The research project is related to three international programs. ETIPAC, which aim is to deorbit end-of-life satellite using electrodynamic tethers. Iperdrone Point 1, that propose to re-entry a capsule from the International Space Station using inner tethers. Internet Space, that propose to develop a new technology based on the use of an electrodynamic tether system for reboosting LEO Earth orbit satellite, and thus for the compensation of the aerodynamic drag. Achieved goals during the last year are the following. For the first program, ETIPAC, the design of the tape spool, the definition of tape mechanical properties and internal components, and the test of the deployer performances through the execution of functional tests. For Iperdrone Point 1 program, the demonstration of the feasibility of moving away from the ISS using tethers, with a particular attention to the hardware and software design. The first part of the second year regarded the study of the spool design. The spool is a critical point for the mission success, and its definition in terms of tension and volume determine the deployment performances. Our trade-off analysis led to the selection of a stationary spool with 3 stacked coils and a parallel spooling. This means that the tape is rolled up around a fixed and central component and no moving parts are present. Its dimensions were preliminarily investigated with the use of a MATLAB code, but further results were obtained with the use of the spooling machine. The spooling machine was used to create the tape spool in order to check its real dimensions and tension. The spooling machine is composed by 2 motors and a pulley mechanism and has the particularity to be able to translate along its longitudinal axis in order to pass from one coil to the next without any interruption. The machine is able to control the tether tension and computes accurately the spooled tape length. During the first year, I investigated tape mechanical properties for 4 tape material: spectra, nylon, PEEK, and aluminium. The goal of my job was to characterize tether materials in order to find out valid solutions for future space tether missions. The determination of the lasting characteristics and damping coefficient were carried out through a campaign of experiments conducted with the laboratory facility Spartans of the University of Padua in Italy. The stiffness and damping coefficient of a flexible line were verified by applying different tensile load profile and then measuring the tether line dynamic response in terms of tension spike amplitude, oscillation decay, and estimation of the damping coefficient. The objective was to reconstruct and compare tests with simulations in order to determine tether mechanical properties. During the second year, the attention was given to a PEEK sample, with a particular focus on the uncertainty analysis on the determination of the damping coefficient. The PEEK tape with the tip mass attached to the free end was modeled as a 1 degree of freedom second order under damped system with a null initial velocity. 3 methods of uncertainty analysis were investigated. Method 1. Nonlinear regression on peak and valleys envelope. Method 2. Logarithmic decrement. Method 3. Linear regressions on peak and valley envelope. For each method, the uncertainty was computed using both the combined standard uncertainty and exceeded uncertainty. The exceeded uncertainty was computed using the t-student distribution with an error risk of 5%, due to the low number of tests that we have, just 9. Here in the picture you can see the results obtained. Taking a mean value from the parameter obtained with the experiment and its post-analysis, I reconstructed and compared tests with simulations in order to verify tether mechanical properties. As you can see, discrepancies between experimental data and simulations are very small and are for large part related to the residual friction between the test table and the module spacecraft unit. Deployment tests were used to check the ability of the deployer mechanism to deploy smoothly different sections of tape. A number of deployment tests on representative tape length were performed to evaluate the system functionality and in particular to check the performances with regard to the following points: specific deployment velocities, transition between the aluminum and PEEK section of tape, velocity ramp up from 0 to 500 rpm of orbitator motor. Tapes were tested at different speeds, and in particular from 30 rpm to 550 rpm. As we will see later, the deployment is always stable and smooth at every speed. Tests were also conducted for the transition between PEEK and aluminum tapes because they have different thickness. These tests proven that there are no issues related to the transition between the two materials, and the dried pulleys can handle the transition without any problem. The velocity ramp-up test was very important to test the initial phase of the deployment maneuver. The test was done from 0 up to a rotational velocity of 500 rpm, and no issues occurred during the acceleration. This slide shows an example of the tape deployment. A dedicated experiment setup was built to suspend the deployer upside down for deploying long tape samples. The upside-down configuration is actually unfavorable for deploying a multi-coil spool because gravity tends to make the outer turn of the coils, not supported by any flange, to fall down. But from the operational point of view, the upside-down deployment has the advantage that the collection of the long tape takes place naturally without the needing of any intervention. Note that if the system works in this configuration, it will work better in waveless conditions. This test was performed for the prevalence velocity of 80 rpm and, as you can see, the deployment is smooth and stable. Hyperdrone.1 program wants to design and develop a small space deployment inner tether system for the orbiting space drone, also called re-entry capsule, with a minimum impact on the space environment from the International Space Station. My attention was given to the baseline design of the auxiliary deorbiting system hardware and software, and is resumed in the diagram on the right. In particular, I studied the feasibility of unwinding a payload away from the ISS using a tether through the study of its dynamics. The hardware conceptual design includes the study of the deployer mechanism, those overall dimensions and concept, thermal and structural analysis performed with the use of ANSYS, and the tether, those the type, materials, length, and size. The software design includes the development of a closed-loop control law to demonstrate the feasibility of releasing a re-entry capsule from the space station, respecting ISS proximity requirements, while minimizing the external contamination. The control law's development was performed with the use of MATLAB. Further studies, not included in the diagram, were conducted on Hyperdrone.1 mission requirements, future project developments, and specifically on cost and development schedules. A very hard work was conducted on the development of the control law based on the swing and release technique. The tether must follow a predetermined reference trajectory in order to reach the desired final conditions suitable to provide a delta V of 20 meters per second at the tether cutting. The block diagram of the feedback control law is depicted on the right, and results on the real control trajectory with respect on the ideal trajectory led us to conclude that moving away from the ISS using tether is not only possible, but can be a real green opportunity that respects all the safety requirements of the International Space Station. As a conclusion, all the pre-established tasks were well achieved, and I can say that I'm perfectly on time with respect to the schedule. What is missing, but this will be investigated during the last PhD year, is to take care of the Internet Space program for the compensation of the aerodynamic drag using tethers. The next year, I will develop current control strategy for navigation and guidance of satellites maintained in the regional orbit by electrodynamic tether system, and I will try to arrive at a solution that is mass efficient and that can generate the desired thrust forces. This slide offers a list of all the publications that regard both the program ETPAC and Iperdrone.